Welcome to Unit 7, Cartesian Vectors, Lesson 2, Dot Product and Work Done. Suppose you wanted to push a heavy box 1 meter along the floor. What's the easiest way to do it? It's always easiest to push the box along the ground when you get low instead of remaining high. Why is that? This is because it is the most efficient way to use energy. The force is the same direction intended for the motion. There is no energy wasted, and work is done. A less efficient use of energy, the force is not quite the same direction as the intended motion. There is wasted energy. There is wasted energy because you are pushing this way, vertically, and also horizontally. So this right here, this is wasted. Least efficient use of energy is if you push perpendicular to the intended motion. There's no movement at all, so I push down, nothing is happening, all the energy is wasted, and no work is done. Here, the middle one, there is some work done. Counterproductive use of energy, the force opposes the intended motion. Movement is in the reverse direction, and negative work is done. So that's really what we're going to be looking at today is we're going to be looking at work done and something called the dot product. Continuing on, so here I have some force and some displacement, and what I like to do is I'm pushing this object 1 meter to the right. So again, there is some wasted motion. Oops. There is some wasted motion right here, and of course that's the vertical force. And there is some work being done, of course, some good force, and that is the horizontal force. So it's actually moving the object in that direction. So this is what we call the productive energy, and this is what we call the wasted energy. Mechanical work is the product of the magnitude of the distance traveled of an object. So this right here, the distance traveled of an object, and the magnitude of force applied in the direction of motion. So here again, my horizontal is my direction of motion. The units are in Newton meters and also commonly known as joules. So if I wanted to calculate the work being done here, it would be displacement times force. And so I am going to have the magnitude of my displacement vector times the magnitude of my force times cos of the angle. And here, since it's 40 degrees to horizontal, so this is 40 degrees here. So it's going to be cos of 40 degrees. So that is my work done. So here I'd have displacement is 1 times the force is 100 newtons, and then cos of 40, because that is the force in the productive direction, and so this would give me, based on my calculator, 76.6 joules. So this right here, this formula here, displacement times force times cos of the angle, is my formula for my work done, also my dot product, which we'll see in a few minutes. All right. The operation is called a dot product. The two vectors A and B, and the dot product is defined as A dot B. So it's like multiplication, but not. So we do the magnitude of A times the magnitude of B, cos of the angle, where theta is the angle between A and B, when the vectors are arranged tail to tail, and the angle is between 0 and 180 degrees. The dot product is a scalar, not a vector, so this is really important here. It is a scalar. So I can't really draw it. You can't really draw a scalar. I can draw a vector, but I can't draw a scalar. And the units depend on the situation. Note, if A or B are 0, that means the dot product is 0. All right, and this is the formula. And this is the formula for geometric vectors. We'll see the formula for Cartesian vectors as well. All right, so we'll do some examples here. Example 1a. Matt pulls a box 5 meters along the floor by applying a force of 150 newtons and the angle is 60 degrees to the horizontal. Find the work done that Matt performs. So again, we can just use our formula. So my formula would be work is equal to the displacement, so it's 5 meters, so 5 times my force times cos of the angle, so here it's 60, since the angle right here is 60. So there is some wasted energy. So here we go, so I'd have here 5 times 150 cos of 60 is 574.5. 574.5 joules. Next one, Max again. Max pulls a sleigh up a hill with a force of 120 newtons at an angle of 20 degrees to the surface of the hill. The hill is 100 meters long. Find out the work Max performs. So again, the same thing. So there is my force. There's the angle to the surface of the hill. So I'm pulling up the surface of the hill is 20 degrees. And then here is the displacement. So this would be my magnitude of D. This is my theta. And this guy right here, this is my magnitude of force. So here my work done is 100 times 120 cos of 20. And so my answer here is 17,276 joules. So therefore, Max performs 17,276 joules of work on the sleigh. So now we're going to check it out in non-application situations. So here, determine the dot product of each pair of vectors. So here, I've got my two. I've got A and B. So here my dot product. So if I wanted to do A dot B, this is equal to the magnitude of A, so 20, magnitude of B, so 30, and then cos of the angle, so cos of 40 degrees. So put this in my calculator, and I get 459.6. There's no units here, or I don't have meters or newtons or anything like that. So there it is, so A dot B. Again, notice there's no direction. It is a scalar, so I don't write direction. It's just a magnitude. For B, so here if I want to do M dot N, this is going to give me 60 times 75 times cos of 90, and watch this, cos of 90 is 0, so the whole thing is 0. The dot, if you want to know if two vectors are perpendicular, you can do the dot product, and it always gives you a magnitude of 0. And then finally, we'll do this one. We'll do V dot U. So V dot U is equal to the magnitude of V, 85, magnitude of U, cos of the angle, cos of 120. And so if I put this in my calculator, I get negative 4,250. Notice here the angle. For an acute angle, I always get a positive value. For an angle which is perpendicular, I always get 0. And then also for an angle which is greater than or between 90 and 180, I always get a negative value. And you'll see that that's one of the nice properties of the dot product. It can always tell you whether the angles are acute, perpendicular, or obtuse. All right, now we're going to look at some properties here. So if I have some properties of the dot product, here's the first one, really important one. If U and V are perpendicular, then U dot V is equal to 0. If neither vector is a 0 vector. It's commutative, U dot V and V dot U. Also the associative property here, K U dot V is the same as K in brackets U dot V. Distributive property, also this is an important one here. U dot U is equal to the magnitude of U squared. So if I've dot two vectors are the same together, I just get the magnitude squared. If I define a vector with the 0 vector, I always get 0. And here we go. This is the Cartesian formula. This is really important. If u dot v for Cartesian vectors, I will get this u1 v1 plus u2 v2. So again, this is for Cartesian vectors. So it's right here. Car vectors. And again, we're going to be using this property a lot, not only in this unit, but next unit as well. Finally, simplify the following. Use the property, to expand and simplify each expression. So ku dot u plus v. So I'm going to distribute this. So I'm going to do this times this, or u that dot that and that dot that. Sorry, it's no multiplication between vectors, but I can do the dot product. So this is going to be k. And I'm going to have remaining u dot u plus k u dot v, which would be equal to k. I'm going to use this property down here. I'm going to use u dot u is equal to the magnitude of u squared, so this is really equal to the magnitude of u squared plus k u dot v. Not much more I can simplify there. Alright, here's the last one. R plus s dotted with r minus s. So again, I'm going to use a little bit of FOIL here. So this dot this, this dot this, this dot this, and this dot this. So with this I'm going to have r dot r, again, is going to be the magnitude of r squared, using, again, this property right here, minus r dot s plus s dot r, and then finally minus, again, I'm going to dot two vectors together the same, so magnitude of s squared. Now, if we notice here, these two vectors are opposite, or these two magnitudes, I should say, are opposite. Negative r dot s and s dot r. So these actually are gone. So I'm going to be left with just simply the magnitude of r squared minus the magnitude of s squared. There we go. Using these properties here, and again, I highlighted the most important ones. First one, u dot v is equal to 0, u dot u is equal to the magnitude of u squared, and finally, u dot v for Cartesian vectors is u1 v1 plus u2 v2. Alright, final question, here we go. Calculate u dot v if u is a Cartesian vector, 5, negative 3, and v is 4, 7, using the dot product, both dot product equations. What do you notice why? There's a nice proof in your textbook on page 373. So the first one, we'll just use a Cartesian vector formula. So here we go, u dot v. So u1 v1 plus u2 v2. So I'm going to simply just dot the first, or multiply the first two numbers together. So 5 times 4 plus, and then here I'm going to have negative 3 times 7. So that's equal to 20 minus 21, equal to negative 1. Alright, so that's the Cartesian formula, pretty straightforward. The next one, here we go, magnitude of u, magnitude of v, cos of theta. So a little bit more complicated. So what I've drawn is, I've drawn my vector u, so this is my vector u right here. Well, this is v, we'll talk about v first, so there's v. Written in the Cartesian form, again, tail at the origin goes to the point here, 4, 7, so this would be 7. And this would be the value 4. And then finally, I've got the other vector, so this is my vector u. And so this guy right here, this is going to be negative 3. And this value here is going to be 5. So what I want to do here is I can find the magnitude of u and magnitude of v rather quickly. Let's do the magnitude of u first. Magnitude of u is equal to the square root of 5 squared plus negative 3 squared, which will give me 25 plus 9, that's root 34. So I've got my magnitude of u. I can also do my magnitude of v, magnitude of v is equal to the square root of 4 squared plus 7 squared. And so here I'm going to get 16 plus 49, which I believe is 65. Now I also want this angle here, because that's going to be my theta. That angle right there is going to be my theta. But of course I can't get theta right now. So what I'm going to do is I'm going to figure out these two angles. I'm going to find out alpha, and I'm also going to find out, let's call this beta. So let's figure out alpha first. I've got this triangle here. Well, I've got my opposite side here is 7. My adjacent side here is 4, so I can figure out alpha. So tan of alpha is equal to 7 over tan of alpha is equal to, not 7, or sorry, 7, yeah, 7 over 4. And so here, if I do that in my calculator, I get alpha is equal to 60.26. Why are you doing this, Mr. Wills? Well, I need magnitude of u, magnitude of v, and cos of theta, so I've got to break up that into 2. Let's do beta. Tan of beta is equal to, the opposite side here is 3. Mr. Wills, it should be really negative 3. No, I just care about the angle, so I'm going to go with positive 3, because that side length is 3, that side length there is 5. If I solve this, I get beta is equal to 30.96. Alright, now I want to go, what is my theta? So my theta will be alpha plus beta. So my theta here will be 91.219. I'm going to a lot of decimal places here because what I want to do is I want to use this formula here, the geometric vector formula. So let's do that. So I know that u dot v is equal to magnitude of u is root 34, magnitude of v is 65, cos of 91.219 degrees, and believe it or not, you may not believe this, but I get, put that in my calculator, kaboom, I get -1. So we can see that the Cartesian formula and the geometric formula will give you the same value. A lot more work here in the geometric vector formula because I've got a Cartesian vector, but we see that the dot product will be the same for either. Of course, we would always use this one. Why? Way quicker than this one here, but I've shown you that they both do work.